Imagine leaving Earth at breakfast, crossing the galaxy by lunch, and watching the birth of a star before dinner. Faster-than-light travel isn't just the dream of science fiction, it's the ultimate question of science itself. But is it possible? Can physics allow us to break the ultimate cosmic speed limit? Or are there hidden loopholes waiting to be discovered? In this video, we'll journey through the science, the paradoxes, and the mind-bending theories behind faster-than-light travel. Question: why does the universe seem to have a speed limit at all? And why, of all things, is it the speed of light? For most of history, nobody thought light had a speed. The ancient Greeks assumed it appeared instantly, the way a fire lights up a dark room without delay. To them, the glow was immediate, too fast to measure. For thousands of years, that idea held. Then, in the 1600s, a Danish astronomer named Ole Rømer noticed something peculiar about Jupiter's moon Io. Sometimes, it emerged from behind the planet later than expected. Other times, earlier. The only explanation was that light itself was taking time to cross space. Rømer was the first to measure it, a speed so enormous it staggered the imagination. Later experiments confirmed it again and again. In the 19th century, James Clerk Maxwell's equations tied it all together. The speed of light wasn't just a measurement, it was woven into the very laws of electricity and magnetism. Light wasn't just fast, it was fundamental. Then came Einstein. In 1905, his theory of relativity didn't just put light on a pedestal. It made light the ultimate reference point for reality itself. According to relativity, the speed of light isn't just about photons. It's the maximum speed for anything. Matter, energy, even information. And the closer you try to reach it, the stranger the world becomes. Your time slows down. Your length contracts. Your mass balloons toward infinity. Pushing something with mass all the way to light speed would demand infinite energy. The universe simply forbids it. This isn't just about physics trivia. It's about the structure of reality. If information could travel faster than light, cause and effect could break. Signals could arrive before they were sent. Messages could be delivered into the past. The very logic of the universe would collapse into paradox. So light speed isn't just fast. It's the guardrail that keeps time, space, and causality intact. But here's the cruel irony. That guardrail is also our prison wall. The nearest star beyond the Sun, Proxima Centauri, is a little over 4 light-years away. At light speed, it's a 4-year journey. With our fastest spacecraft today, it's more like 70,000 years. Crossing the galaxy? Over 100,000 years. Reaching the edge of the visible universe? Longer than the universe has even existed. To human ambition, the speed of light is a cosmic tease. It lets us see the stars but not touch them. It dangles the universe in front of us, then slams the door shut. And yet humanity has never been content with limits. Once people believed no object could move faster than sound. Then came the jet engine. Barriers fall, rules bend. So is the light speed barrier truly absolute? Or is it just another frontier, waiting for a deeper understanding? For now, Einstein's law stands unbroken. No object with mass may reach or exceed the speed of light. But physics is full of hidden corners, wormholes, warp bubbles, exotic energy, quantum quirks. They whisper of loopholes, ways to bend the rules without technically breaking them. Before we explore those, remember this: every photon, every radio wave, every glimpse of starlight in the night sky has obeyed this one law since the dawn of time. The cosmic speed limit is the heartbeat of reality itself. And that's why, if faster-than-light travel is ever possible, it won't just change how we move. It will change everything we know about space, time, and what it means to exist. When we talk about the speed of light, we're not just talking about how fast something can move. We're talking about the nature of time itself. Einstein's theory of relativity revealed a truth that sounds impossible, but is proven every day in physics labs. Time is not absolute. It bends, stretches, and twists depending on how fast you move. Imagine you're on a spaceship accelerating close to the speed of light. For you, time inside the ship flows normally. You eat, you sleep, you age. But for someone watching from Earth, your clock runs slower. Hours for you could be years for them. This isn't science fiction. It's been measured with atomic clocks on jets and satellites. Time literally ticks differently depending on your speed. This is called time dilation, and it's not just a curiosity. It means that if you could travel close to light speed, you could experience a journey to a distant star in just a few years of your own time, while thousands of years might pass back home. Now picture what happens if you try to push further. The faster you go, the heavier you become. Your mass grows. The energy needed to accelerate you skyrockets. At 99% of light speed, you already need staggering amounts of energy. At 99.999%, it's nearly infinite. And to actually reach light speed, infinity itself. This is why scientists say nothing with mass can cross that threshold. The universe would demand more energy than exists, but relativity doesn't just place a speed limit. It also twists our understanding of cause and effect. Imagine if you could somehow move faster than light. In one frame of reference, you might be going forward in time. In another, you'd be going backward. Events could flip. Messages could arrive before they were sent. Cause and effect would lose meaning. Reality would unravel. That's why physicists are cautious. It's not just that faster than light travel is hard. It may be that faster than light travel is forbidden because it would break the logical spine of the universe itself. And yet, this is where the paradox of human ambition comes in. We've always chased what seemed impossible. Flight, space travel, the splitting of the atom. Each breakthrough redefined what we thought the laws of nature allowed. So when we talk about faster than light travel, we're not just testing the limits of technology. We're testing the very boundaries of time and causality. To ask, can we move faster than light, is really to ask, can we rewrite the rules of the universe itself? And that's why the next step in this story is so tantalizing. The idea that maybe, just maybe, we don't have to break the limit. If we can bend space itself. When people imagine faster than light travel, one idea instantly comes to mind: the warp drive. Born in the pages of Star Trek and carried into the dreams of millions, it's not about rockets or engines in the traditional sense. It's about bending the very fabric of reality. Here's the basic problem. Einstein's relativity won't let us move through space faster than light. But Einstein also gave us another gift: the realization that space and time themselves can bend, stretch, and ripple. Gravity curves space around stars and black holes. If space can bend under the pull of mass, could we learn to bend it on demand? That's where the warp drive comes in. Instead of pushing a ship through space at impossible speeds, a warp drive changes the space around the ship. Imagine a bubble where space itself is squeezed at the front and stretched at the back. The ship doesn't move inside the bubble. Instead, the bubble rides the wave of curved space. To an outside observer, it looks like the ship is traveling faster than light. But locally, inside the bubble, it never breaks the rules. This wild idea leapt from science fiction into real science in 1994, when physicist Miguel Alcubierre published a paper showing that such a warp bubble was mathematically possible. His equations suggested that relativity itself might allow for a loophole, a way to surf space without violating the speed limit. But there's a catch, and it's a big one. To create a warp bubble, you need something called negative energy or exotic matter, not just a little of it, potentially an amount greater than the mass energy of entire planets or stars. And exotic matter isn't something you can scoop up or manufacture easily. It may not even exist in usable form. Even worse, there are questions about whether a warp bubble could ever be started or stopped safely. Would it trap anything inside? Would it destroy what it touches? Would it collapse catastrophically? The math leaves as many questions as it answers. Yet despite these daunting obstacles, the warp drive idea refuses to die. NASA researchers have even studied whether clever geometries might reduce the energy requirements to something more reasonable, maybe the mass of a starship instead of a planet. It's still speculative, but the fact that relativity doesn't outright forbid, it keeps the dream alive. And the dream matters, because the warp drive represents something more than an engine. It's the ultimate symbol of human defiance. Relativity slams the door in our face. The warp drive whispers, maybe we can find a window. For now it remains a theory, a tantalizing what if. But if one day we learn to bend space at will, the stars themselves could fall within our grasp. Still, bending space isn't the only loophole science has imagined. There might already be shortcuts waiting for us, natural tunnels through space-time itself. If warp drives are about bending space, wormholes are about skipping it altogether. Instead of traveling across the universe, what if you could take a shortcut through it? A wormhole is a tunnel in space-time, two distant points connected by a hidden passage. The idea first appeared in 1935, when Albert Einstein and physicist Nathan Rosen found a strange solution to Einstein's equations. It looked like a bridge between two regions of space-time. Today we call it the Einstein-Rosen bridge, or simply a wormhole. To picture it, imagine the universe as a sheet of paper. If you're an ant crawling on the surface, two dots at opposite ends seem far apart. But fold the paper, press the dots together, and suddenly they touch. That's the dream of a wormhole, folding space so distance vanishes. If such passages exist, a spacecraft could leap across the galaxy in an instant, without ever breaking the speed of light locally. To outside observers, the trip would look impossible. To the traveler, it would feel no stranger than stepping through a doorway. But wormholes, like warp drives, come with baggage. The first problem is stability. Most theoretical wormholes collapse almost instantly, snapping shut before anything could pass through. To hold one open, you'd need exotic matter with negative energy, just like the warp bubble. The second problem is safety. If the walls of a wormhole are unstable, they might shred anything inside with infinite tidal forces. And then there's the most unsettling problem of all: time. A traversable wormhole doesn't just connect points in space. Depending on how it's manipulated, it could connect different points in time. In theory, you could travel not just across the galaxy, but into the past or future. That opens the door to paradoxes, meeting your past self, preventing your own journey, or changing history itself. And physics, so far, seems deeply allergic to paradoxes. Despite these problems, wormholes remain a serious topic in theoretical physics. They appear naturally in equations of general relativity. They're studied in connection with black holes, quantum gravity, even string theory. No one has ever seen one. No evidence proves they exist, and yet, the math refuses to rule them out. For storytellers, wormholes have become iconic. From Interstellar to Stargate, they are the ultimate cosmic shortcut. For scientists, they are tantalizing possibilities, clues that space-time may be stranger and more flexible than we can yet imagine. If warp drives are engineering solutions, wormholes are nature's hidden tunnels. Both offer a way to outwit the speed of light without violating it directly. But both demand physics far beyond our current reach, and so the question lingers: are wormholes real gateways to the stars, or just illusions written in math? While we don't yet know, the search for FTL doesn't end here. Because beyond the bending of space and the folding of time, there's another possibility. Particles that were born to outrun light itself. Warp drives bend space. Wormholes tunnel through it. But what if there are particles that never needed such tricks? Particles that were born faster than light. In the 1960s, physicists proposed just such entities, tachyons. The very name comes from the Greek word tachy, meaning swift. Unlike ordinary matter, tachyons wouldn't creep toward the speed of light. They would already exist beyond it, racing forever in a realm we cannot reach. Here's the strange part. According to relativity, nothing with mass can accelerate past light speed. But relativity doesn't forbid particles that already live on the other side of that barrier. Their world is simply alien to ours. They would never slow down to meet us. They would forever remain superluminal. If tachyons exist, their physics would be bizarre. Their energy decreases the faster they go. At infinite speed, they would have zero energy. Their presence could destabilize quantum fields, unravel causality, and even allow signals to move backward in time. A tachyon, in theory, could send a message before it was written, an idea that bends not only physics but logic itself. For decades, tachyons have existed more as speculation than evidence. They've appeared in equations of string theory. They've served as mathematical tools in quantum field models. They've even been tested experimentally. Scientists have looked for tachyon traces in cosmic rays, in particle accelerators, in the fabric of neutrino experiments. But every search has come up empty, and yet the allure remains. If tachyons were real, they might explain mysteries like dark energy or the quantum entanglement that seems to defy distance. They could offer the first natural path to faster-than-light communication. No warp bubbles, no wormholes, just particles whispering across the cosmos at impossible speeds. But tachyons also carry danger. If they exist, they could unravel the very consistency of physics. The universe might protect itself by forbidding them outright. Or perhaps tachyons exist in ways we cannot yet see, hidden behind dimensions or phenomena we barely understand. Science fiction has eagerly seized on the idea. Tachyon beams, tachyon signals, tachyon drives, they've become the shorthand for FTL solutions when writers need a touch of plausibility. But in reality, tachyons remain ghosts of mathematics, a whisper that maybe, just maybe, the universe has faster pathways built into its foundations. Still, tachyons highlight a recurring theme in our search for FTL. The deeper we go, the more time itself begins to twist. Because whether through warp bubbles, wormholes, or tachyon signals, one truth keeps surfacing. Breaking the light barrier isn't just about speed. It's about causality, about whether events in the universe follow an unbreakable order. And that brings us to the next chapter, a world where faster than light doesn't just mean space travel. It means time travel. When we dream of faster than light travel, we imagine starships leaping across galaxies, explorers reaching alien suns. But physics whispers a darker secret. If you can outrun light, you can outrun time itself. Einstein's theory of relativity ties space and time into a single fabric. Go faster than light and suddenly, cause and effect begin to blur. What looks like a forward journey in one frame of reference may appear as a backward journey in another. In other words, faster than light motion could allow communication or travel into the past. At first glance, this sounds thrilling. Visit yesterday. Send a message to last week. Warn yourself of a disaster before it happens. But hidden in this dream are paradoxes so severe they could tear logic apart. The most famous is the grandfather paradox. Imagine you travel back in time and prevent your grandfather from meeting your grandmother. If that happens, you were never born. And if you were never born, who traveled back to prevent the meeting? The loop collapses into impossibility. Another is the causal loop. What if information sent into the past has no origin at all? Suppose you receive the blueprint for a warp drive from your future self, then build it, and one day pass it back to your younger self. Where did the blueprint truly come from? Nowhere. It exists without origin, a ghost of causality. These paradoxes aren't just philosophical riddles. They strike at the foundation of physics. A universe where cause doesn't reliably lead to effect is a universe without stability, without rules. And so many physicists believe nature must prevent time travel. Perhaps through mechanisms we don't yet understand. Stephen Hawking once proposed his chronology protection conjecture, the idea that the laws of physics will always conspire to prevent time paradoxes. In his view, quantum effects would destabilize wormholes, warp drives, or tachyon channels the moment they threaten to allow backward time travel. The universe, in essence, would guard its timeline, and yet, not all physicists agree. Some suggest that paradoxes can be avoided if the universe follows a principle of consistency. In this view, you could travel to the past, but you could never change it. Whatever you do, your actions were already part of history. You might try to stop your grandfather from meeting your grandmother, but something would always intervene to preserve the timeline. Others propose parallel universes as an escape hatch. If FTL creates paradoxes in one universe, perhaps the act of changing the past simply spins off a new branch of reality. Kill your grandfather, and you don't erase yourself. You simply create a timeline where you were never born, while your original self continues in another branch. But these are speculations stacked upon speculations. To this day, no experiment has shown evidence that FTL travel or backward time travel exists. The math tempts us, but the reality remains elusive. And so the paradoxes remind us of the stakes. Faster than light travel isn't just about spaceships moving quickly. It's about rewriting the order of events, bending time into loops and forcing us to question whether the universe even allows such freedom. Whenever science hits a wall, we turn to the quantum world. Because down there, among atoms, particles, and waves, the universe plays by rules so strange they almost feel like science fiction. And if there's any place where faster-than-light possibilities might hide, it's here. One of the strangest quantum phenomena is entanglement. Imagine two particles born together in a single quantum event. No matter how far they drift apart, across a lab, across a galaxy, measure one and the other responds instantly. Albert Einstein himself was unsettled by this, calling it spooky action at a distance. At first glance, entanglement looks like faster-than-light communication. But here's the catch. Entanglement doesn't transmit usable information in a way that can break relativity. The instant correlation is real, but to actually communicate, you still need a normal, slower-than-light signal. The universe keeps its speed limit intact. Or does it? Some physicists wonder if deeper layers of quantum theory, ones we don't yet fully understand, might eventually reveal a loophole hidden inside this spooky connection. Then there's quantum tunneling. Normally a particle shouldn't cross a barrier. It doesn't have the energy to climb. And yet in the quantum world, particles sometimes tunnel through barriers as if they simply vanished on one side and reappeared on the other. Experiments show tunneling happens so quickly that mathematically it seems to involve faster-than-light processes. But again, there's debate. Most physicists argue no actual information crosses the barrier faster than light. It only looks that way in the math. Still, these phenomena hint at a deeper truth. Our universe may not be as rigid as Einstein's equations suggest. Quantum mechanics has already rewritten our understanding of probability, measurement, and reality itself. Could it someday rewrite the light barrier too? Some researchers have even explored whether quantum fields might support exotic states, negative energy densities, vacuum fluctuations, that could stabilize wormholes or power warp drives. Others wonder if hidden dimensions, predicted by string theory, might allow shortcuts that bypass the speed limit in our observable universe. And then there's the most unsettling idea. What if the speed of light isn't truly constant in all conditions? Some cosmological models suggest that in the early universe, light itself may have traveled differently, opening the possibility that the cosmic speed limit could be more flexible than we believe. At present, every quantum loophole we've tested seems to preserve relativity's rules. No experiment has yet broken the light barrier. But quantum mechanics is still an unfinished book, its final chapters unwritten. If a path to FTL exists, it may not lie in rockets or engines. It may lie hidden in the probabilities, fluctuations, and mysteries of the quantum realm itself. And if that's true, then the key to the stars won't be built. It will be discovered. But science doesn't exist in isolation. If humanity ever does uncover an FTL loophole, whether in warped space, wormhole tunnels, or quantum tricks, the consequences will ripple far beyond physics. Because the moment we master faster-than-light travel, the universe isn't just bigger. The universe is ours. Imagine it. One moment, humanity is bound to a single world. The next, the stars are open. Faster-than-light travel isn't just technology. It's a revolution as profound as fire, agriculture, or flight. It is the moment humanity leaves its cradle forever. The first impact would be exploration. With FTL, our solar system becomes a backyard, and nearby stars, Proxima Centauri, Alpha Centauri, Barnard's Star, become reachable destinations. We would send ships not just to visit, but to settle. Colonies on alien worlds, stations orbiting strange suns, humanity scattering like seeds across the galaxy. But with expansion comes conflict. Who controls the first FTL drive? A government? A corporation? A single nation? Or is it shared by all? History shows that new frontiers often spark rivalry, competition, and war. The Age of Sail brought both discovery and conquest. The spacefaring age could be no different. Entire planets might one day be contested territories, fought over not for land or gold, but for habitable atmospheres and resources beyond imagination. Then there's culture. FTL wouldn't just change where we live, it would change how we think. Imagine looking up at the night sky and knowing that friends, family, entire communities exist out there on worlds orbiting distant suns. Our definition of home would expand. Nations might fracture. Cultures might diverge rapidly as colonies adapt to alien environments. A human born on Earth and a human born under the light of a red dwarf may share ancestry. But over centuries they might feel like entirely different peoples. Economics, too, would transform. A single habitable exoplanet could hold resources greater than Earth itself. Interstellar trade might emerge, but only if FTL travel is cheap and stable. If not, colonies could become isolated, developing unique economies, and perhaps breaking away from Earth's authority. And what of philosophy? For millennia, we've asked if we are alone. With FTL, that question wouldn't remain hypothetical. If intelligent civilizations exist among the stars, faster-than-light travel all but guarantees we would find them, or they would find us. First contact could unite humanity in a way nothing else ever has. Or it could shatter us if our first meeting ends in fear or war. There is also danger in FTL itself. A technology that can bend space-time or pierce wormholes could be weaponized. A ship that can cross light years might unleash destruction on planetary scales. The line between starship and superweapon could blur. The survival of civilizations may depend not only on discovering FTL, but on controlling its use responsibly. And yet, the promise is irresistible. With FTL, humanity steps into its true destiny, a multi-planet, multi-star species, no longer confined to a fragile world orbiting an ordinary sun. With FTL, extinction from a single asteroid, war, or climate catastrophe would no longer spell the end. We would have outgrown our vulnerability. The impact of faster-than-light travel is nothing less than the transformation of humanity itself. It would be the beginning of our cosmic age. But as we dream of this destiny, we must ask a sobering question. What if others have already walked this path? What if FTL is the key to understanding not just our future, but the silence of the cosmos? Where is everybody? That was the question physicist Enrico Fermi famously asked in 1950. The universe is vast. The Milky Way alone holds hundreds of billions of stars. Many of those stars host planets, and countless of those planets lie in the habitable zone. Statistically, there should be civilizations among them, perhaps millions, and yet silence. We have scanned the skies for decades and no one answers. This silence is the Fermi paradox. Faster-than-light travel is one of the sharpest edges of this mystery. Because if even one civilization developed FTL, the galaxy should be teeming with life. With warp drives or wormholes, it would take no time at all on cosmic scales for a species to spread across the stars. Colonies would multiply, outposts would grow, civilizations would expand like wildfire. Within a few million years, a blink in cosmic time, an FTL-capable civilization could fill the Milky Way. So why don't we see them? Where are the cities glittering on alien worlds? The starships streaking across the void? Why, when we gaze up at the sky, does it remain so profoundly empty? Some argue this is proof that FTL is impossible. The silence may not be a mystery at all, but evidence that the cosmic speed limit is absolute. No matter how advanced, no species can leap between the stars faster than light. In that case, civilizations remain trapped in their own neighborhoods, too far apart ever to meet. Others suggest the silence hides something darker, a great filter. Perhaps civilizations do discover FTL, but the technology is inherently unstable, destructive, or uncontrollable. A single mistake could annihilate entire planets. FTL might not be the gateway to the stars. It could be the final test, one most civilizations fail. And yet there's another possibility. Perhaps civilizations with FTL are out there, but they choose not to reveal themselves. They may see us as too primitive, too dangerous, or too fragile to join a galactic community. We might be under quarantine, observed but untouched, like animals in a preserve, unaware of the watchers beyond the trees, or maybe the silence is an illusion. Our instruments are young. Our search has only just begun. What if the signs of FTL civilizations are subtle, hidden in physics we don't yet understand, signals we don't know how to recognize, structures we mistake for natural stars? The Fermi paradox forces us to confront an uncomfortable truth. Either FTL is impossible, or it is possible, but comes with consequences so profound that no civilization survives or dares to use it openly. And so, as we dream of warp drives, wormholes, and tachyons, we must ask, are we chasing a future that others before us have already reached and been destroyed by? For as long as we've looked at the stars, we've dreamed of reaching them. Faster-than-light travel is the ultimate expression of that dream, the promise that distance is not a prison, that the infinite night sky can become a map, a network of roads, a home. Science tells us that FTL is forbidden, or at least hidden behind walls of energy, paradox, and impossibility. And yet, time and again, loopholes appear in the equations. Warp bubbles, wormholes, tachyons, quantum tricks. The future of FTL may play out in many ways. Perhaps it is impossible, and humanity will forever be bound by the light barrier, expanding slowly across our solar system, but never beyond. Perhaps it is possible, but only through physics so advanced it will take centuries, even millennia, to master. Or perhaps the first breakthrough will come suddenly, unexpectedly, a discovery that transforms us overnight from a planetary species into a galactic one. But whatever the path, one truth is clear. FTL is not just about technology. It is about destiny. To master faster-than-light travel is to decide what kind of civilization we will become. Will we use it to explore peacefully, to share knowledge, to preserve life? Or will we repeat the mistakes of history, expansion fueled by conquest, greed, and war, magnified across the stars? The dangers are real. A warp drive could become a weapon. A wormhole could destabilize reality. FTL communication could unravel causality itself. And if the Fermi paradox warns us of anything, it is this: the stars may be silent because civilizations that reach too far, too fast, do not survive. Yet, the dream remains irresistible. Because within that dream lies hope. The hope that we can outgrow the fragility of a single world. The hope that extinction is not inevitable. The hope that humanity's story can stretch across millennia, across light years, across the galaxy itself. And so we stand at the edge of knowledge and myth. Faster than light travel may be forever beyond us, or it may be the very key to our survival. We do not yet know, but to seek it, to study it, to imagine it, is to embrace the very spirit that makes us human. Because every great leap in history has started with a question. And tonight, we are left with the greatest question of all. Not can we go faster than light, but what kind of future will we choose if we ever do?